Good morning, everybody. Thank you so much for coming to this session, and I'm really excited to close out and talk to you today about some work we've been doing on some lunar zircons from 14321. I think Lars has set it up pretty well, so I'm ready to jump into things. I will start here then. So just to give a quick overview, since we've already gotten a pretty great overview, Zircon was known mostly to be a robust geochronometer, and we've used it to date lunar samples and understand our reconstruction and timeline and evolution of lunar crustal building events. However, we now know that Zircon poses many potential issues when we're just trying to obtain ages and interpret them at face value. Specifically, when talking about the moon, we're worried about shock events and how that affects the zircon grains. Those shock events can then disturb the uranium to lead system in them, and then that in turn affects the grains that we obtain. And now we know that it can push them to be actually older or younger than their true age. And if that wasn't hard enough, lunar zircons are mostly detrital, and so geological context is kind of hard to sometimes get for them. And so one way we're trying to overcome this issue and address it is to actually go into the grain for this context. And so we're doing micro and nanostructural analysis on these lunar zircon grains from lunar Breccia 14321 in order to determine if the age information that we're getting from them is reliable. So 12 of these zircon grains were separated out of 14321, and then lead ages were obtained on them. Then we were sent the 12 grains. We used SEM for preliminary analysis. We did EDS maps and EBSD on each of the 12 grains. Then we chose a subset of 4 of those zircon grains from which we took 2 focused ion beam sections out of each. So we have 8 FIB sections in total. And then we've been looking at those FIB sections using TEM and STEM techniques. And overall, what we're trying to understand is what are the range of nanostructures that we're seeing between the grains, but also between the FIB sections, what processes produce the features that we're seeing, and then overall trying to understand how it all ties in and what that means for the ages. So when they obtain the lead ages on these 12 grains, as you can see from this plot that Lars Borg made, they span over 300 million years in age in total. And so the question is, are they representing some type of continuous geological event? Is there resetting going on? Are they meaningless? What's going on? And so these are the subset grains that we chose to take the FIB sections out of. I only have 3 up here because we have only gotten to look at these 3 grains thus far. So the SIMS spots are the dark areas, and each of the ages are listed in white next to them, and the red lines represent where we took those FIB sections. We tried to take them as close as possible to those SIMS spots. And so we have grain number 2, which is our quote-unquote younger grain, grain number 6, which is one of our older grains, and grain number 11, which is kind of an intermediate to old grain. We try to choose grains from different ages of the age spectrum as well as kind of intermediate as well. So now to get into what we found so far. So the first thing I want to mention is that we found mottled contrast that's present in all FIB sections of the grains that we've looked at thus far. Mottled contrast is attributed to the process of metamictization taking place. So essentially, as those radioactive elements are decaying in the structure, it's destroying the structure, which are those dark domains. But what you can see is that the mottled contrast seems to vary in each of the grains, which with our grain number 2, our quote-unquote young grain, exhibiting more mottled contrast than our quote-unquote older grain from grain number 6. Now I'm going to get into grain 2, as this has most of the features that we've seen so far. So this is kind of the first inclusion that we found, our first feature. I think it kind of looks like biological. It occurs along a subgrain boundary, and in the lower portion in its little tail, there is some glass. In the middle portion, there is a calcium-rich pyroxene, which you can see much better in the EDS layered map on the right. And then kind of in the upper middle portion, zoomed in the red box, we have titanomagnetite, and you can actually see the faceted edges, which I just think is really amazing. But we did find this inclusion. We also found these 2 other features. So feature number 2, it was a void that occurred on the edge of the FIB section and was surrounded by a silica-rich glass. Silica-rich glass has been found by, I believe, Kuziak et al. 2022 paper in another lunar impactite zircon. So silica-rich glass has been founded in lunar impacted zircons. This third feature are faceted voids that occur along another subgrain boundary that we found in the fib section. These are similar to what was also described in Kuziak et al.'s 2022 lunar zircon impactites, and they also found these faceted voids. These have also been found in another zircon from 14321 from a Crow et al. 2019 paper. However, those voids were actually filled with material. Now for the big one, we found these lead nanoparticles in both fib sections of grain number 2. I'd like to apologize because in my abstract, I call them lead oxide nanoparticles. However, we are still trying to constrain what phase they are, whether they're lead metal or lead oxide. So I will just be calling them lead nanoparticles for the time being. We did find a few of them in the first fib section. However, we found much more in the second fib section. They seem to be randomly distributed throughout the fib sections, but they are definitely there, and they do occur close to each other, and they seem to all be about 20 nanometers in diameter. But these indicate lead mobility in the system, which is a really huge finding. This has been recently found last year in a 2024 paper in a lunar zirconolite. However, other than that, they've only been described in lunar or in terrestrial zircons. Now in grain number 6, we did find this linear feature that occurs in the very middle of the fib section. We are still trying to constrain what this phase is. It's been a little hard to get an EDS analysis on it. However, this may be indicative of shock as it is occurring just straight down the fib section. But until we know what that phase is, we can't 100% sure understand maybe what process took place. For grain number 11, I did, briefly mention it, but we did not find any nanostructural features other than that mottled contrast. So I unfortunately don't have any other pictures to show you for that grain. So just to kind of summarize and wrap up, both grains number 2 and 6 have nanostructural features that are indicative of shock. However, the shock effects seem to be distributed heterogeneously throughout each fib section. And so because these features vary not only between fib sections in the grain, but between grains, we need to just understand what shock pressures they did feel and exactly how much it may have disturbed the grain. Now for grain number 2, those lead nanoparticles indicate that lead mobility, and that is a really important finding when we're trying to understand if the ages we've obtained are reliable. In grains number 2, 6, and 11, once again, had that mottled contrast, which is attributed to the process of metamictization. We need to constrain exactly what degree of metamictization has been experienced in each grain and how that may attribute to the issue with ages possibly. But overall, what I would conclude right now is that grain 2's number ages are most likely not reliable because of this lead mobilization and all of these inclusions that we're seeing from shock most likely. For grains number 6 and 11, further work is going to be needed to constrain exactly how disturbed they may be and therefore understand what their ages may mean. But what I'd really like to leave all of you with is that interpreting lunar zircon ages is not straightforward and it's not easy, and it needs to be done with caution. We need some context for these grains. So doing nano and microstructural analysis gives you really good context for understanding what those ages may mean, if they mean anything at all. And thank you so much.